conjugates. Conjugate acid-base pairs is what we're going to focus on. So basically, when you define a reactant as an acid or a base, what it did to become that acid and base. So the product of what it did is going to make it a conjugate. So we see that the acid here in our example, the HCl, is the one it's going to give up a proton. Because it's giving up a proton, we know it is a Bronston and Lowry acid. It's giving up that H plus. After it gives up that H plus, so as a product, it's the Cl minus. So we call that the conjugate base. So the acid is going to pair with the conjugate base. What a conjugate means is if that reaction were to go backwards, notice this arrow is a two-way arrow. If it were to go the other direction, this chlorine would be accepting the proton, and accepting the proton is what a base does. So that's why it's the conjugate. It's basically going the other direction makes it a conjugate. So going in the forward reaction, we name them as acid and base. Going in the backwards reaction, we name them as conjugates. And a lot of times we'll even say like a conjugate pair, meaning that if the hydrochloric acid is an acid, then its conjugate pair, the Cl minus, the chlorine ion, is the conjugate base. We also talk about conjugate acid. So that was conjugate base. It pairs with the known acid. The conjugate acid then pairs with the base. So here's an example of a bunch of bases. We have NH3, OH minus, H2O, and CO3 2 minus. We really don't even need a reaction to know what the conjugate acid would be. So if you remember, a base is defined as accepting a proton. So if NH3 got another proton, it would be NH4 plus. So that would be its conjugate acid, because it's again what happens after it's performed its basic duty, like the thing that made it a base. So again, NH3 is going to accept the proton, therefore it's a base. After it accepts the proton, it becomes the conjugate acid. Hydroxide here, OH minus, is going to accept a proton. After it accepts the proton, HOH or H2O water, it becomes the conjugate acid. H2O, after it accepts a proton, it becomes H3O plus, again, a conjugate acid. And then our carbonate ion, is CO3 2 minus. It's going to accept one proton and become HCO3 minus. So instead of being 2 minus because that hydrogen was positive, it's now 1 minus. So the conjugate is again after the hydrogen was added for bases. We do reference strengths, like how you know which direction a reaction is going to flow. We look at the strengths. If the reactants are stronger than the products, it's going to flow forward. If the products are stronger than the reactants, it's going to go backwards. If they have like mixed strength, that's usually when you have like weak stuff, that means it's going to go both ways. So that's what I kind of defined for you here is you have this relative chart. So if you look like across, it's the conjugate. So if I have the acid in the conjugate base, the acid is giving up the proton, it's donating it, so the conjugate base, and then you can see their strength. So OH minus it's our Arrhenius like basic ion, so it has the least amount of acidic character. That means its conjugate base is the strongest base we could possibly have. So really the strong acids down here, those are going to be the one way because there's, like I said, they're strong. When you have weak is when you go back and forth you find like an equilibrium within your reaction. So essentially our strongest acids down here at the very bottom of this picture are going to create our weakest bases, and vice versa. Our strongest bases will create our weakest acids. So I've used the term a couple times now, amphoteric, when I've been talking about water. So as I said, it can act as either an acid or a base. There's a couple compounds that can do it, not just water, but the other ones are mostly ions. So mostly polyprotic ions that are like in the middle of their dissociation. So when you have like one H or even two H's with a charge, a negative charge specifically, then you know you can continue to give up H's or continue to add them. So like with this example here of HSO4, or I'm sorry, this bottom one here, just the HSO with a -1. If we got rid of another hydrogen, we would have that -2. There should be a 4 here. That's just a typo. If we added a hydrogen, we'd get rid of the negative altogether because that hydrogen would cancel out that negative. So this version of the ion is amphoteric. This one is not. You can only add hydrogen to this. You can't take any away because it doesn't have any. And then same thing here. This one is also not amphoteric. You cannot add a hydrogen to this. It won't create any stability. It won't hold, but you can take it away. So only this middle one is actually amphoteric, where it can act as both an acid and a base. It can go both directions. Here's an example of how water would act as a base in this first picture, where it's with something that is a stronger acid. So the hydrofluoric acid is a stronger acid than water. Therefore, it's the one going to act as a water. It's going to donate the H into solution, giving us the H3O+. So their water acted as a base. Here, the water is the stronger acid, so it's going to be the one to donate the hydrogen, giving me H2S and OH minus. So in the first one, we have water acting as a base. In the second one, we have water acting as an acid based on whether it's donating or accepting a proton.